Hey everyone, welcome to my channel on Physics Tutor for SATs, IITs and GRE. And today I'm going to be solving another conceptual physics problem on free body diagrams. So let's see what we have given over here. There is a system where there are two masses, small m and capital M, and they are suspended through strings over a pulley, and the whole system is at rest. It also says that there is a friction coefficient at both contacts as mu. So if you see my previous videos, we had solved similar problems without friction. Now there is a friction to account for. So what we have to find is, if the system is at rest, what's the maximum value of the ratio of these masses, capital M by small m, and also discuss a situation when tan of this angle theta, which the incline makes with the ground, is less than the friction coefficient mu. So I've discussed this approach before in my previous videos, so check it out if you have to, which is why I have these diagrams ready on the free body diagrams. And again, check out the videos to understand why these forces exist in this manner. Now, if we draw the free body diagram of M on this horizontal incline, there has to be a tension T pulling it towards the right. This whole system looks like having a tendency of slipping to the right. So there is a tension pulling it. And then there is a normal reaction which the ground exerts on it, N1. The weight is mg downwards. And just because there is friction, it is trying to pull it back, trying to balance the force or the tension T in the string. So it has to be backwards. So this is a free body diagram for small m. Now let's see, for this system to be at rest, forces in all directions must balance, right? So let us say that in the horizontal direction, forces to the right, which is T, is equal to mu n1, which is forces to the left. And if you see in the vertical direction, we can say that n1 equal to mg, forces in the upward and the downward balance, which both of them implies that tension here equal to mu times mg. So we have eliminated the value of n1 here and got the value of t. Now similarly, if we look at the second free body diagram for capital M, we see that the force mg exerts always vertically downward. There is a normal reaction into perpendicular to the incline, because the incline is exerting it against the body. So like we have discussed before, there is a tension pulling it upwards, trying to hold the body from falling off. And again, there is a friction coefficient, so it is also trying to pull the body up so that it doesn't slide down. So both of these forces are trying to keep the body stationary against sliding down the incline. Again, we have discussed in the previous videos on how these components along this slide would be mg sine theta and perpendicular to the incline would be mg cos theta. Again, feel free to check out my previous videos to understand how we got these components. Now, if you again equate the forces along the incline and perpendicular to the incline, it's always easy to do that. You can always choose any other direction, but then it's easy to choose the directions which are parallel to the incline and perpendicular to the incline. So again, if we say that the upward forces must downward the downward forces parallel to the incline, then we get the equation as T plus mu n2 equals mg sine theta, and the upward forces perpendicular to the incline is n2, which equals the downward forces, which is mg cos theta. Now again, we can say that tension here is mg sine theta minus mu n2, or we can say that it is mg sine theta minus mu mg cos theta. Simplifying a little bit, we say that tension equals mg sine theta minus mu cos theta. Now we got the equation earlier, which says t is mu small mg, and now we are getting again another value which says, so this is equation 1 and this is equation 2, which says that the tension is this value. Now if we equate these two, we simply get mu mg equal to capital Mg sine theta minus mu cos theta. Now if we look at the question, it asks about capital M by small m, so we can cancel out g here and say that capital M by small m equal to mu by sine theta minus mu cos theta. So this is the maximum value that can be obtained here if all the forces must balance and the system is not sliding. Okay, so now let's get to the second part of the question, which asks to discuss the situation when tan theta is less than mu. Now, if we get to that part and say that tan theta is less than mu, we can also represent that as sine theta by cos theta less than mu, or say that sine theta is less than mu cos theta. Now let's look at this body here and see the forces and say that assume that this body never slides down. No matter what the conditions are, this body never slides down. We can take other assumptions and prove as well, but for simplicity I'm taking this. We can also assume that the body always slides down and kind of write the equations there. For simplicity, let's take that this body will never slide down in any condition, which means that the net upward forces along the incline is always going to be greater than net downward forces. So we can say that t plus mu n2 is always going to be greater than mg sine theta. We know t is from equation 1, which is mu times mg, plus mu n2, we can take the value of m2 from this equation here, which is capital Mg cos theta, which is now greater than mg sine theta. And we can say that mu mg is greater than mg sine theta minus mu cos theta. I just took this term towards the right hand side. Now we can cancel out g here. And now you would see that if sine theta is less than mu cos theta, given the assumption, then this entire term becomes negative. But this term on the right hand side is a multiplication of mu and m. These are always positive, coefficient of friction and mass. So this is a positive value. Now this comes out as a general thing that a positive number is always greater than a negative number, which is always going to be true. Which means that this scenario is always going to satisfy that t plus mu n2 is going to be greater than mg sine theta with this assumption, which means that the net upward forces is always going to be greater than the net downward force, which also means that the body will never slide down, no matter what the value of theta or mu is, in case this assumption is being satisfied. So that's it for this problem. So we discussed these two situations, and if you liked anything about it, please do comment or let me know if you want to understand some specific type of problems in free body diagrams, and we can take it from there. Until then, take care and bye.